Okay, we are on lesson 7.4, exponential growth and decay. So in this section, we're really trying to make use of our integrals and differentiation, mostly differentiation, to see how it is applicable in what we do in terms of applying it to science, most importantly, and applying to more of the everyday life that we usually ask about, when are we ever going to use this, right? So the law of exponential exchange says that there's a relationship between your growth and or your decay, and the formula is this: y equals y naught. Y naught is your initial amount, e to the kt. So, if you're thinking, oh, this is a brand new formula, it really isn't. What you learned before in other classes, mostly Algebra 2 and Trig, is A PERT. A equals P e to the RT. This was a compounding continuously function. So it's actually the same thing. P is the principal, how much you put in initially. Y naught is how much it was there initially. You have this E exponential function that's going to help you with your the rate of change. And then the rate at which you're getting your interest is the same as the rate at which things are happening, growing or decaying. So that's where your K is. And T is time, right? T is time. And A is what the amount now, and Y is the amount now. So in these cases, your K is the rate at which things are happening. So if it is growing, your K is going to be greater than 0. If it is decaying, your K is going to be less than 0. And keep in mind that when we were dealing with interest back then, your T has to be in terms of years. However, when we're dealing with exponential growth and decay here, it really doesn't matter. Well, not doesn't matter. It follows whatever the information is given. So it could be days, it could be weeks, it could be seconds, it could be years. It could be a lot longer than that. So you have to look at what the equation is giving you, okay? Half-life is something we deal with a lot in science. So there is a shortcut here. If you're looking for the half-life of a certain thing, it is a quicker way to do it would be take natural log of 2 divided by K. Now, if you don't know if you don't want to use that, this is just kind of an extra information that is a lot quicker than figuring out what the half-life is. You can definitely figure it out using the equation and looking at the information given to you. The last one is this Newton's law of cooling. Typically, this is given to you, but again, it's kind of nice to know how to use this, and we'll see it in our example. All right. So just a reminder of using our separation of variables. And it does remind you to say that indicate with the domain over which the solution is valid. So we're going to have to see what is happening here. Okay. So separation of variables. Notice how I have 2x here and have a y here. You want to move the y to the left side, and you want to keep the x's on the right hand side. So dy, moving the y over, will divide by y, and you have 2x multiplying the dx over. Okay. And to get rid of our dy's, we take our antiderivative. Remember, dy over y makes the natural log of y, because that is 1 over y, or y to the negative 1, right? And on the right-hand side, you get x squared plus c, okay? Now, you can go ahead and plug in your initial value. It tells you y equals 3 when x equals 0. So natural log of 3, x equals 0. So I'm going to have natural log of 3 equals 0 plus c. So c is natural log of 3, okay? Now I'm going to go ahead and plug it back in. I have natural log of y equals x squared plus natural log of 3, right? And so then if I want y by itself, I go ahead and take e to the power of natural log, because that will help me get rid of the natural log very nicely. And since y is by itself, we don't have to worry about the y being absolute value in this case, because it says y equals 3. It actually kind of already forces our equation to be in the positives. There are cases where the absolute value actually makes a lot of sense to check in, but we don't have to worry about that for now. Okay. And then you have e to the x squared plus natural log of 3. When you have addition in your exponents, remind yourself you can split it. So e to the x squared times e to the natural log of 3. And the whole goal is this should reduce down and bring down the 3. So you have y equals 3 e to the x squared. E to natural log will reduce out. All right. So if you're looking at this function here, this final equation, e to the x squared. Remember, e to the whatever power is looking like this, right? It is asymptotic to the x-axis. In terms of domain, though, there's no issues. Left and right, there's no asymptotes. There's no vertical asymptote. So my equation is very nice, and my domain It's all real numbers. Okay. All right, next equation, same idea. You have dy equals cosine, dy over dx equals cosine squared x. So since this one has the y, this one has to move to the left-hand side. You have dy divided by cosine squared y equals dx. All right, you need to take the integral, of course, to integrate this and get rid of your dy's and dx's. Now, 1 over cosine squared, we can't really do cosine squared, but we can remind ourselves 1 over cosine squared is really secant squared y dy. And don't forget, on the right-hand side, there's really a hidden 1 there. You can't really see it. So this becomes tangent of y equals x plus c. And this, at this point, right, secant squared is the antiderivative of secant squared is tangent. So this works out very nicely. Plug in 0 and 0 for our x's and y. So 0 and 0. So I have tangent of 0 equals 0 plus c. Tangent of 0 is very nice, it's 0, so c equals 0. Hence, my answer is tangent of y equals x. Now, remember, we did this in our practices. To get rid of our trig functions, you need to use tangent inverse, right? Tangent inverse of this, so that then reduces out each other. So you have y equals the tangent inverse of x. Again, you've got to remind yourself, tangent function looks like this. Tangent inverse function actually looks like this, right? Kind of like a cube root function. So in terms of x's, there's still no problem here. It goes left infinity, right to infinity. So the domain of this is all reals again. Okay, no issues. Again, remind yourself, domain only has issues in 3 different cases. Number 1, the denominator equals 0. Number 2, when your even roots are not positive, inside the roots not positive is negative, so you can't take the root of that. And any of your log or natural log has to take positive argument. So you cannot take anything 0 or negative inside the log and natural log. And that's when you will have issues with your domain. Okay. All right, our favorite, we have our word problems to really see how this is being used. All right, so it says find the amount of time for a $2,000 investment to double if the annual interest rate is compounded annually, monthly, quarterly, and continuously. So I reminded you what the formula is for continuously. That's the APERT formula. The other 3 has the formula of your interest, or your final amount is equal to P times 1 plus R over N. R is the rate, your interest rate. N is how many times it's compounded to the T times N. Okay, so we're going to use that for part A, B, and C. So for part A annually means N equals 1. Okay, so for an investment to double, that means I end up now with 2P instead of P, my original, double my original, right? 1 plus R over, here's my rate. Rate is 8.25%. Got to change it to 0.0825 because that is the decimal amount. So 0.0825 over 1, because that's what N is, to the T times 1. First thing, the P's will reduce out because you divide by P on both sides, it's gone very nicely. You're left with 2 equals 1.0825 to the 1 power, to T power. So how do we get that down? Remember, when you have your variable in the exponent, you use log. That's the whole point of having log. Log allows you to access what's an exponent. So at this point, you can use log, base 10, or natural log. Personally, I like natural log, but really at this point, this is just kind of your preference, right? So natural log of both sides, what does that do? It allows you to say natural log of 2 equals T comes down because that's an exponent. Natural log of 1.0825. And divide both sides by natural log of 1.0825. So the time it takes is natural log of 2. We have a natural log of 1.0825, and that is approximately 8.744 years. Remember, when you're dealing with interest, your answer is always in terms of years. Okay? All right, let's compare that to monthly, right? If you compound monthly, you are compounding a lot more times than yearly. Annually, you compound 1 time. Monthly, you compound 12 times because there are 12 months. So in this case, N equals 12. Okay, so the same thing, you want to double your investment. So you want 2P now, right? 1 plus 0.0825 over 12, and then 12T, right? Your N is 12. right? So again, same as before, your p's should really reduce out really nicely. You're left with 2 equals, and in this case, you could go ahead and divide it through. So 0.02825 divided by 12 added to the 1, it's approximately 1.006875 to the 12t, right? Okay, so same thing as before. If we do natural log of both sides, I'm able to bring down the 12t. So natural log of 2 equals 12t, natural log of 1.006875. So if you divide natural log of 2 by 12 and natural log of 1.006875, that would get you the t. So t is approximately, I can look at this, 8.431 years. So it makes a bit of a difference, 0.3 year difference. So about 3 months difference, a little more than 3 months difference, but still difference, right? So compounded monthly is going to be a little bit faster than compounded annually. So compounded quarterly, that exactly the way it sounds, quarter means cutting a year into 4 parts. So n equals 4. So you can probably expect quarterly is going to be slower than monthly, but faster than annually because I compound 4 times rather than 1 time, and I'm compounding 4 times than 12 times, right? So it's going to make a difference there. Okay, you're doubling your investment. P1 plus 0.0825 over 4 to the 4t. The p's are reducing out, right? And so you have 2 equals 1 point, and if you divide that through 0.20625 to the 4t, so natural log of both sides, bring down the 4t, natural log 1.020625. So t is natural log of 2 divided by 4 times natural log of 1.020625. If you're punching this in the calculator, be careful if you're punching this in. You actually want to do natural log of 2 divided by 4 and then divided by natural log of 1.020625. If you want to put both of them in denominator, you got to put them in parentheses because otherwise your calculator is going to do order operation. It's going to divide by the 4, but then end up multiplying by the natural log if you don't put that in parentheses. So watch out for that. This will give me the time to be about 8.488 years. So remember what we said, it's a little bit faster than, slower than the monthly, but faster than the annually. Okay, so obviously nothing's better than continuously, because continuously you're doing this continuously, right? So your equation is 8 pert, so you want double your investment, PE to the R 0.0825 T, right? Same as before, the P's should really reduce out because it doesn't matter where your principal is, you want to double that. And now you have 2 equals E to 0.08225 T. So the compounding continuously is the only one you have to use natural log because of an E function here. For parts A, B, and C, to get the exponent down, you can actually use log if you want. Again, I like to use natural log because it's just quicker for me. So natural log of both sides, that would give me natural log of 2. And then on the right-hand side, you're left with 0.0825 T. So divide this over. T is natural log of 2 divided by 0.0825. So how long will it take to double? 8.402 years, right? So they're relatively close. I think mainly because your interest rate is really high at 8.25%. It's never this high. So the amount of time is not going to make a huge difference. If the rate is different, then the compounding will definitely make more of a difference, right? If it's a little bit lower, okay? Okay, suppose that cholera bacteria in a colony grows unchecked according to the law of exponential change, meaning it follows the 8 pert formula, or that formula you saw in the front, whereas y equals y naught e to the kt, right? The colony starts with 1 bacterium and doubles in numbers every half an hour. How many bacteria will the colony contain at the end of 24 hours? Okay, so what you want to do is use this first information. The colony starts with 1 bacterium and doubles in number every half an hour. Okay. Your formula is A equals PE to the RT, or KT, doesn't matter. So it means that it doubled, it started with 1, it doubled. And then at the rate, I'm not sure what the rate is, but I know that the time was only half an hour, right? Because I'm using the same unit, half versus 24 hours, so half an hour. So if you're trying to solve for K, you're trying to solve for the rate, right? So divide by 1 on both sides, you get 2 equals e to the r over 2. Okay, take natural log of both sides to get the e to be gone. So you have natural log of 2 equals r over 2. Last but not least, multiply both sides by 2. So natural log of 2, natural log of 2 is my rate. Okay. Now, from that, I'm going to write my equation. I want to figure out how many bacteria will the colony contain at the end of 24 hours. Okay, so what is the amount? I don't know, but we started with 1 bacterium. E, my rate is 2, natural log of 2, T. Okay, you want E and natural log of 2 to be next to each other. So it would be a very wise idea to rewrite it, because when you're multiplying on the exponent, you can move things around. And the reason why I want to do that is because now this E to the natural log of 2, that E and the natural log reduces out and the 2 drops down to a base. So really this is 2 to the 2t. So your equation is much easier. The 1 multiplies everything, it's gone, right? So this piece right here makes the 2 come down as a base, but this 2t still remains in the exponent. Now you can answer the question. How many will the colony contain at the end of 24 hours? So how many at the end of 24 hours? 2 to the 2 times 24. So 2 to the 48 power. That's going to be a lot of bacteria, depending on the power of your calculator. It is 281474976710656, which is, some calculator will give it to you like this. 2.815 times 10 to the 14 bacteria. So lots and lots of bacteria. Okay. All right. The next problem says the decay equation for radon 222 gas is known to be this equation. And this is my K, right? But because it's decay, my K is 0.18. The negative just tells me it's decay. The K itself, the negative tells me it's decay because it's going down. The K itself is the 0.18 with T in days. About how long will it take the amount of radon in a sealed sample of air to decay to 90% of its original value? What is its half-life? So in this case, I'm actually going to answer the second question. What is its half-life? Because if I recall in the second box above in my notes, half-life is equal to natural log of 2 over K. So I simply take natural log of 2 and divide it by my K here, and I will get 3.851. And now to look at my units, these are days. So this particular element decays really quickly. In roughly 4 days, it's going to decay to about 50%. Okay. All right. So then if I look at this and say, all right, it wants me to know how long it would take to decay to 90% of its original value. So here's my awesome equation, right? Here's my awesome equation. So if I want 90% of the original value, I have 0.9 of the original value now. And I started with the original value, e to the negative 0.18 t. So when you know you want a percentage of the original doesn't matter how much. You can just reduce them out. So now you have 0.9 equals e to the negative 1.18 t. Natural log of both sides. So natural log of 0.9 equals negative 0.18 t. Divided by negative 0.18, divided by negative 0.18. How much time will it take? About 0.585 days. So about half a day, right? Because it takes about 4 days to get it to half-life. So if I don't want half, I want 90% of what I have now. It's just going to take a lot less than that. It's going to be about half a day, a little more than half a day. Okay. All right, last problem here. The temperature of an ingot of silver is 60 degrees above room temperature right now. 20 minutes ago, it was 70 degrees above room temperature. How far above room temperature will the silver be 15 minutes from now? Okay, so you're going to use the information given to you that it is 60 degrees Celsius right now, 20 minutes ago. So it started out as 70 degrees Celsius, right? So you're looking at it in terms of, this is still using the, it's still using the exponential rate decay because we don't know what the room temperature is. That's why we're still using this formula up here, the law of exponential change. If we do know what the room temperature is, then we're going to use the Newton's law of cooling here. because we don't have that extra piece of information, okay? So I'm going to use what we have here to write my equation. So right now it is 60 degrees Celsius. 20 minutes ago started out at 70 degrees. E to the K, that took 20 minutes, right? All right, and because this is the temperature is decreasing, we know my K is going to be negative. If my temperature is increasing, my K is going to be positive, okay? All right, first things first, we're going to solve for K because you're going to use information given to you to write your equation. So you got to solve for K first like we did in number 4. Divide by 70 on both sides. So you get 6 over 7 equals e to the negative 20k. Take natural log because now you want to get rid of your e and access whatever's there. So natural log of both sides. Natural log of 6 over 7 equals negative 20k. Last but not least, natural log of 6 over 7 over negative 20 equals k. You want to keep your equation as complete as possible. So you really don't want to reduce out your k right now. You want to keep it in this form because we're going to clean it up in a minute. Okay, so then now that we have this, we can use that to write our equation, right? So before we even answer A, we're going to write our equation and say, right, so we have y equals the original temperature, 70 degrees. Actually, no, right now is 60 degrees. So, okay, we're going to use not 670 as my base. So we're going to use 60 as my baseline. E to the negative k, so negative k. So negative k, so your k is natural log of 6 over 7 over negative 20, and then you have your t here, okay? Now, the negative will reduce out. It's normal, 60e. And you want to rewrite this so that the natural log is right next to your e. So natural log of 6 over 7, and you have t over 20. Again, that way this will reduce out. Bring down the 6 over 7 as a base. So 6 over 7, t to the t over 20 power. And that will be the equation we're using because it says 15 minutes from now. So what I need to do is just plug in the 15 for t. So for part A, I simply go y equals 60, 6 over 7, 15 over 20. So that's 60, 6 over 7 to the 3/4 power. All right, put that all in the calculator. And yes, none of this you are expected to do by hand. You're going to plug this in the calculator and get your approximation for your answers because you can't do this by hand. All right, so your temperature now will be about 53.449 Celsius, right? All right, answer the next part. What about 2 hours from now? Okay, now remember your units are in minutes, so make sure you change that 2 hours to 120 minutes. Still 2 hours from now, so still 2 hours from 60 degrees. So y equals 60 degrees, 6 over 7, 120 over 20. So that's 60, 6 over 7 to the 6th power, right? So if I do that, I get a temperature that's much lower, 23.794 degrees Celsius. So it's decreasing very, very quickly, exponentially, right? When will a silver be 10 degrees above the room temperature? So when will the silver be 10 degrees, basically, right? So we're still using now. Now it's 60 degrees. So part C, the silver is 10 degrees now, right? And my equation was 60, 6 over 7. And we have t over 20. Okay, you're solving for t. So first thing you want to do is divide. Make sure you always get rid of this coefficient first. So you have 1/6 equals 6 over 7 to t over 20. At this point, your exponent is up there on top. So you want to use log or natural log. Same thing again, I'm going to use natural log. So natural log of 1/6. Bring down the exponent, natural log of 6 over 7 like so. Okay. And then it's kind of up to you what you want to do first. I'm going to multiply both sides by 20 to get rid of the 20. So 20 natural log 1/6 equals t times natural log of 6 over 7. So then t is 20 natural log of 1/6 over natural log of 6 over 7. Please watch out how you're punching this in. Make sure you are trying it yourself to make sure you are understanding where the parentheses go and where the numerators and denominators are. And you should get approximately 232.469 minutes, right? Because our units are in minutes, but that doesn't make a lot of sense for us. So if you want to, you can divide that by 60. So you can get about 3.874 hours. That makes a lot more sense to us. Okay. I believe your homework does have a problem on the Newton's law of cooling. So make sure you go through that and know how to use that. Again, I believe when you are given a problem like that on the AP exam, they do provide that equation for you. Okay. All right. That's it.